bright spots here is what is left over of your current connector of your terminal. And around it you have all sorts of corrosion leftovers. This is often some form of lead oxide as well, but on the wrong electrode. So on the negative electrode we established we have lead, pure lead as metal, and if that corrodes you also have lead dioxide, as you have on the positive electrode, but on the negative electrode it actually has no chance in participating in your reaction. So that is actually there bad. You can see the corrosion in this example is very advanced. So your current collector in this case corrodes, and the less current collector you have, I think it's clear, the stronger your resistance is increasing. So the more corrosion, your internal resistance increases, means again the same, either you have less power available, or at the same power, with increasing resistance, you have much higher temperature evolution. And with high temperature, you again accelerate one of the other aging processes, and so on and so on. This, of course, is irreversible. So, irreversible effect. Then, water loss. Last main aging reaction. We established already that water is being formed during the main here, so lead dioxide, sulfuric acid turned to lead sulfate and water. That is fine. However, there is a side reaction from here. This water can also dissociate, as we had it, into hydrogen and oxygen. Yeah, just because, as I said, we are above the electrochemical stability limit of water. So that actually happens. It is one main aging effect, and one further problem. As you see here, who of you knows what the problem is when you, let's say, you release hydrogen and oxygen in the air? Anybody? It's actually, this mixture is very explosive. So hydrogen-oxygen mixture is really explosive. There's a name for it. I don't know it down anywhere. I think not. I don't know the English word. I think it's something like hydroxy reaction or something. In German, it's actually called Knallgasreaktion, which translates to bang gas reaction. So it really makes a huge bang, and that is a really big issue. If you think about, for example, closed systems, as we established, they are not open to the atmosphere, there is no gas exchange, meaning if this type of gas mixture forms within the very small airspace you have of your battery, you very fast come to a concentration of this gas mixture that can explode. So for open batteries, the issue actually is not as severe. You do not release as much of this gas from a small battery if it's placed in a room like this. And typically, if I remember correctly, the concentration that you have of this mixture in normal air is 5 to 75%. In this region, if you have 5 to 75% of the air in this room is filled with a mixture of hydrogen and oxygen, then this is combustible. You then ignite the match or anything, you have a big issue. Above 75 or below 5%, actually, it is not possible for this to be ignited. It's also for flooded type batteries, also an issue, but much, much smaller of an issue than for closed type batteries. Another thing, as you see, is water loss. So water is really, everybody, we require water. It is not toxic. You can touch it, you can drink it, whatever. So you can actually refill the water. So nothing more happens really. You lose water, and that's it. That means your acid concentration, of course, is increasing compared to the water content, but you can just go ahead with a cup and refill the water in your battery. I don't know, who of you, maybe your parents, they told you that it was typical a couple of decades ago to refill actually your batteries in your, that you have at home, in your scooter, anywhere. It was very critical. There's even a small opening that you can open and just take a cup of water and refill it. Yeah, no, we also still have it, not for automotive batteries. Yes, but all of these, let me go back quickly. These type of batteries, they all have openings to refill the water. Or they even have a water level sensor and automatic refilling of water. So then that is very helpful, as you can imagine. Meaning this aging effect is reversible. Usually not fully reversible. No, you don't put acid in it, you put pure water. It needs to be, of course, distilled water, so it should not contain any charge carriers on its own. But you don't need to use acid with your water. Because you only use water, all of the acid is not evaporated. So you can use this distilled water, you can get it almost everywhere. Of course, for VILA, a glass net or so, that doesn't use liquid acids, this will become difficult, as you cannot refill something in a glass net which is not really liquid by itself. So for these types of batteries, water loss is an irreversible agent.
Is this a remedy for this kind of side?
What is the remedy? Refilling the water?
To avoid the exclusion condition. Can we have some amount of sweat?
No. So refilling the water will not help you in preventing any explosive gas mixtures. We will see it later, but refilling of that this reaction exists, let's say, is very helpful actually. So it's a gating mechanism, yes, but that this reaction, the higher your voltage, the faster is this side reaction. Meaning it is really tough to overcharge a lead acid battery, to really charge it to voltage levels that kill the battery. And that is also why for lead acid batteries typically you do not require balancing systems. So because if one battery is a little bit higher in voltage and the other one is a little bit lower, means for the one with higher voltage, this reaction is a little bit faster and slowly the voltages will again come close to one another. So it's an aging mechanism, yes, but also quite a necessary side reaction to make the acid batteries more useful. Yes. One last word. For closed systems, there is actually a thing called recombination. So it's a little bit counterintuitive, for me at least. Once you have hydrogen and oxygen gases somewhere in the airspace here, and it cannot escape, actually it can happen, and it can happen at quite a big rate, that these two recombine to water. Depending on the conditions, of course, you can have condensation, for example, if it's quite warm outside, the humidity is quite high, and so on. So recombination also is a thing for closed systems. It doesn't prevent water loss completely, but it for sure slows down the water loss for closed systems. Okay, any questions? So summary. So just the four causes again, and what accelerates them, and the consequences. Yeah. Could you mention that maybe we will ask this tomorrow in the exam, if you want to look at something. So for corrosion, they are accelerated by higher voltages, by temperature, and by cycling, by using your battery. So just using it, you have corrosion. As a consequence, your resistance increases and your efficiency reduces. Then sulfation is accelerated if you full charge your battery not very often, very seldomly, if you have high depth of discharge and if you have high acid stratification. The consequence is that you have higher over voltages, meaning your battery voltage overall is reduced. And that's just to mention, we said it yesterday, actually, for lead acid batteries, the best condition to be in for minimum aging is actually very high state of charge. So 85-90% aging speed is greatly, aging speed in terms of capacity loss is greatly reduced. Completely opposite from lithium batteries because of this effect. Then we have erosion, loss of active material, so it's caused or accelerated by mechanical stress, corrosion, gassing. Consequence is capacity loss, makes a lot of sense, and actually what you also have, you increase your risk of short circuits. So when lots of conductive material falls down here, so it can happen very likely that the separator is destroyed and actually you form electric connection in between plus and minus. And water loss, or also can be seen as a self-discharge, is actually accelerated, there we have it again, by antimony poisoning. So, brief word on it. As you know, antimony is a catalyst for all types of reactions and also for the side reaction of oxygen-hydrogen evolution. So if you have antimony in your alloy of your current collector, and that is, for example, by corrosion exposed in larger quantities to the electrolyte, so your water and your acid, that means this reaction is accelerated. That is meant with antimony poisoning. Because it acts as a catalyst. You can have micro shorts always. Somewhere there is somehow a small hole or in your separator, or you have an electric connection in a very, very small area. It doesn't necessarily mean that your battery is fully dead immediately, but for sure it increases all types of side reactions. And yes, loss of water generally is a bad thing, because worst case, when you use a lot of water, the top of your battery actually is dry. And when it's dry, it doesn't touch electrolyte, it will not participate in the reaction anymore, and then you lose capacity. But yes, it's reversible, certain times, reduce efficiency, and you can, if you're not careful, also if you use more water, freezing. Okay, so summary, pros and cons of side reactions. So amp-hour-based efficiency drops with side reactions because not all of your charging or discharging current goes into your consumer. Yes, you have an explosive gas mixture forming with hydrogen and oxygen. Yeah, I got it. Oxy-hydrogen reaction is in English. So 4 to 75% concentration is highly explosive and it's a very, very big explosion. So I don't know if you're in your bachelor's, do you have physics usually or not? Yes?
Yes.
Yes, so in our physics courses during bachelor usually they have a huge cannon. Yeah, so they put a ball inside, a huge steel cylinder, and then they have 2 tanks with oxygen and hydrogen, and they fit it behind the ball and put a letter to it, just to show. And the ball just flies hundreds of meters. It's actually quite fun. If you are interested, you can Google it. These are very, very dangerous explosions. Yes, so what's bad as well as the water generally is not, of course, you have corrosion can increase, it slowly causes, yes, I don't know why it's here, it doesn't have what causes corrosion causes lead oxide, of course. And advantages that you have is that overcharging your side reactions actually are boosted because they are just favored at higher voltages. Large overvoltages you can avoid, so no balancing needed, and you also don't need single cell voltage monitoring. What you have for lithium battery, so for each cell in a series connection you have their own voltage measurement. For lead acid, it's completely uncommon to have it. As you know, with our integrated battery sensor, we have measurement for our automotive batteries under battery, but it contains 30 single battery cells. So it's not 30 single cells, but 5 or 6 in series. So if that would be lithium, we would require 6 voltage sensors. And so what is also possible, I don't know if you have ever seen like these stationary lead acid batteries. Actually, when you look closely, you can see the formation of oxygen and hydrogen that, in the batteries themselves. You see bubbles and the bubbles rising to the top. This bubble creation and then it rises to the top actually also counters purification, because it mixes your electrolyte and has quite a positive effect on the overall lifetime in this regard. One word about thermal runaway. So we know thermal runaway from lithium-ion batteries. There is also the thermal runaway for lead acid batteries. So generally, what is the word thermal runaway? Because it is nowadays used so often. It means the heat or the thermal effect, it runs away. Basically, it means it's accelerating, and you do not need to input any form of heat anymore, but the heat increase happens on its own. That is just meant with it in battery charging overall, and that you have this of course is an effect, but it almost never happens, because we know about this effect. First of all, you can implement temperature control and say if the temperature rises above a certain point, stop charging. This can be done. If you do not have temperature control, you can also just limit your CV phase artificially by time. And to say, yes, I want to do CV phase, but please stop after 1 hour. And then usually also nothing happens. So this can be countered quite easily, but it can happen. It doesn't need to be that you have a fire, because it's a water-based system. Fire breaks out quite late. First, you need to lose all of your water. This can happen if you are not careful and you don't witness that anything is happening. Then maybe you run the risk of fire, or at least melting of your materials and capacity loss. But typically, depending on how long this goes on, you can recover your battery. It's not fully empty. Okay, one word. We had this slide yesterday. That one actually is very typical to use in lead acid batteries. So CCCB and second CC stage afterwards. And this is done to counter your aging effects that we just had. We want to really be sure that the sulfate, so the sulfate crystal state is solid. And that you can do if you increase your voltage a little bit above the typical operating voltage. It is not harmful, as we established, because we have the water oxide reaction. So this is a typical charging strategy in lead acid batteries. And I think what you yesterday this typically is not implemented as you see it here with a constant current as a second phase, but as a trickle charge. Yeah. So trickle charging goes like this. It is also CC, CB, CC, if you want so. However, this CC phase is not in a constant current, but very short pulses. And yes, you should be able to answer if you use very short current pulses. Your individual pulse actually can be much higher than a constant current that you would apply, because your RMS current in the end is smaller. So this is very common, very established, and I think everybody has if you plan on not using your battery for a longer time, you usually always hook it up to a charger, right? Because we keep it at 90% so it doesn't die. And usually this is a charging strategy implemented for lead acid batteries. Completely different to lithium, yes?
Does the frequency of the pulses matter at all?
No. So this is, I think you cannot call this frequency. Usually this is a time domain just the pulse. How often you do it and how high the pulse depends on the battery always. But you can do this more often or less often. You just should not overheat your battery. That's the only reason. Yeah, so typically, I always have to get my head a little bit into it. So that acid, as I mentioned, is established for 100 years. And they have their own set of words that they use to describe the battery. So just as an example, typically you give current limits, not as a current, but as a current for per 100 amp hours. So typically a CC phase for formative batteries usually is 16 up to 40 amps per 100 amp hours. So if you have a 500 amp hour battery, typically you should not exceed. It's a little bit weird, but that's just naming convention. There's no real technical reason for it. And usually cars, they have much higher power densities, up to 120 amps for each 100 amp hours you use. And then normally the voltage, the CD phase, is set to 2.4 cell voltage. As I mentioned, usually without temperature measurement, although it would be very useful, but normally it is too complicated and almost nobody has the ability to measure temperature and to hook it up to a control circuit that the temperature actually triggers something. So normally you are left, if you do the first step, you are left with 92% SOC. So these numbers appear to be very concrete numbers, but actually this is very concrete. So this is true for almost all applications, as I mentioned, fully standardized technology, and this is why these numbers are not random numbers, but this is true for almost all technologies and all applications you find. It's very convenient. And then, yes, you switch again to a trickle charging, usually around 4 amps for each 100 amp hours. As you see, these pulses are much smaller than the initial CC current that you are using. And then you are going into trickle charge to counter aging effects, sulfation and electrolyte mixing by water creation. Okay. One word on something that is unique to lead-acid batteries: dynamic charge acceptance behavior. Ever heard about it? So charge acceptance is something that is not existing for lithium batteries. For lead-acid batteries, it means how much charge in amp hours can my lead-acid battery actually take in. For example, for regenerative braking, when you have it as a stationary plant or so on. That is an important parameter. And here is how you test charge acceptance. So usually you discharge your battery up to 0%. This is randomly done, but you want to know your behavior. And at every 10 SOC steps, you measure your dynamic charge acceptance. Yeah, so this is done to emulate regenerative braking in the microhydrates. So this is just a very typical testing cycle for charge acceptance because it's not similar but very close to how regenerative braking would come to our battery in the microhydrate. And this is the result. So you see two curves. We see here SOC on X, on Y is DCA. You can also learn this abbreviation for dynamic charge acceptance. Completely established term, given as N per amp hour, again, only for the acid battery. So, if you are discharging, so you come from 100% and you go down with your SOC, you see that you are somewhere in the medium region, and meaning you can accept roughly 0.3, a little bit more amps for each amp hour. So for a 100 amp hour battery, it means just about 30 amps you can push into your battery. If you discharge, you see that, let's say at 70%, you are just below 0.5. So for the same 100 amp hour battery, you could push 50 amps into the battery. And just by having SOC difference of 20%. But this feature is unique to lead acid batteries. And it increases a little bit more. What is more drastically and more interesting for me, if you charge back again. So now you are at the low state of charge, you charge your battery, you start again at a very similar charge acceptance, dynamic charge acceptance. However, the higher you charge your battery, you have a huge drop in dynamic charge acceptance. That means, roughly you are around 0.1, and that means for 100 amp hour battery, you could only charge it with 10 amps. That is actually very significant, especially for microhybrids, regenerative braking, start-stop, and so on, and especially for cranking. So let's assume, nice. I don't know, I'm going skiing in the winter holiday. I drive somewhere where there's a lot of snow, some Himalaya maybe. It's very cold, very high. You arrive there, you say, I will stay for 2 weeks. Nice holiday, and for 2 weeks I will not need my car. And you say, I'm smart there, I studied. I will hook my battery up to a charger, so it's at 90% SOC. So I can be sure that the cranking goes well after 2 weeks of not using it. However, you have this effect, and it might very well be that your car will just not start, because it's not possible for your car to accept or deliver more amps directly after charging. So it's actually quite important to remember. It is an effect, but it can be handled as well quite well, as you would imagine, with the correct profiles, with the correct algorithms, how to handle what, and so on. So this is an effect, but it's not a major cause of concern. The cause for this is actually that the capacity of the battery for lead acid depends very strongly on discharge rate. And this is the effect. In this magnitude is only present for lead acid batteries. What you see here, temperature over capacity. And you see here two curves at different discharge rates. And you can see here for a 2C discharge, you have a certain capacity over temperature, and for 0.1C discharge, you have a much higher capacity available. Yeah? And these are not minor effects, as you can see. So in between 2C and 0.1C, you actually have something around 50 percentage points of capacity availability. That is a huge difference. You have a rule of thumb. With every Kelvin or with every degree Celsius, you lose 0.6% of capacity. One more word on these weird numbers. It's again an acid thing. It is fully established. We use 0.1C, 2C, 5C for current rates, whatever. The acid guys, they have something different. They say I have a current of I10 or I20 or I5. It's the same logic, but the other way around. So an I5 means I have a current that charges or discharges my battery in 5 hours. And discharging in 5 hours for lithium batteries, what we are used to, would mean a current rate of 1 divided by 5, 0.2C. Which just is a similar description, but the other way around. If you are dealing with lead acid batteries, also in data sheets and so on, the currents are always given in this type of notation. There's a problem actually, or something that runs exactly opposite to each other, that e-motors usually require higher currents at low temperatures. Sorry, I made a mistake. It's not only e-motors. I will correct it. So you don't get confused. So it's not only e-motors, it is ICE engines as well. temperatures all of the oils used in motors, be it cooling oil for electric motors or cooling for ice and so on and so forth, it gets more viscous. So it's less liquid. And this is why everything that is turning and gears and whatnot, it's a little bit more difficult. And this is why usually the currents are starting at cold temperatures for cranking, or also to provide currents to e-drives at low temperatures is a little bit higher. Okay, just so that you have seen it. It is the same message as before, so no new information. This is something that you find for lead acid batteries in data sheets and so on. I just wanted to show it to you because, as I said, for lead acid is just a different community. They do things differently, but with the same content. So on here you can find how much energy can I discharge out of my battery at a certain operating point. Discharge energy here, voltage level here. And if you now want to assess whether or not this battery is useful for my application or not, you can look at these curves. For example, you say, yes, I will operate at a medium voltage of 2 volts. Typically, my discharge current is I5, for example. That means you come around at 350 amp hours. So 0.1 times I10 does not equal I100. So you cannot calculate like this. Should be obvious, but you very easily come to ideas like that. So you have standard values. I think it's not too important to remember, but usually, if you are another topic, sorry, the current for lead acid batteries very often is called C, not I. I don't know why, but it's here not the capacity, but the current. It's super weird, but it's just a naming convention. I don't know why that is. So if you have 10 times the current of I10, roughly equals to half the current at I10. And that means I1 is roughly 7 times I10. As I said, capacity on charge. Capacity on charge current is for lead acid batteries by far the most strongly dependent. And as I said, C has been established to talk about all of these relative currents. It's very confusing. Just keep it in the back of your head. Whenever you see C in the context of only lead acid, it might not mean capacity. Okay, the last word on what we just mentioned. With decreasing temperature here to the right, the required current by your, in this example, e-motor is actually increased. For this specific example, at minus 20 degrees, actually, this specific engine required double the amount of current to run. However, on the other hand, coming from 25 at minus 20 degrees, the capacity you get out of your battery is actually 50% less. So these are fully opposite trends. You need to take it into account. However, it really rarely happens that you want to drive an e-motor at minus 20 degrees with a minus 20 degree battery. So this use case almost never happens, but if you're somewhere in the beginning here, you also have already one last word on how actually does discharge curve of lead acid battery look like. We didn't touch it yet.